Alrighty. So let's start with a brief introduction to phasors. So in the frequency domain, electrical engineers had developed a shorthand notation So let's say that we have the following generic signal. Let's call it V of t is equal to Vm, where Vm is the magnitude cosine omega t plus some phase angle theta v. And similarly, we could represent a current, a time domain current as Im cosine omega t plus some phase angle theta I. So these are our time domain representations. We can use Euler's identity. And say that V of t is simply the real part of the complex number Vm, sorry, no cosine there, e to the j omega t plus theta v. And similarly, I of t is the real part of the complex number Im e to the j omega t plus theta I. And I call this the mixed domain. There's not really a good name for it. It's still technically in the time domain because there is a time dependency explicit in our functions. So we have not fully moved over to the frequency domain. So that's why I call it the mixed domain. And we can do circuit analysis in this domain, but it's usually avoided because the frequency domain is so much easier. Lastly, we can convert into the frequency domain by taking our mixed domain representation and defining a phasor voltage V as Vm angle theta V, which is identically equal to Vm e to the j theta V. And we can define a phasor current as Im angle theta I, which is identically equal to the complex number Im e to the j theta I. So to convert, sorry, let me write this down. This is the frequency. That should be a C, not a G. Domain, or commonly referred to as the phasor domain. So to convert a time domain signal into a frequency domain signal, we simply keep the magnitude, keep the phase angle, and suppress the frequency component. And we're able to do this because we know that if we only have excitation at one single frequency, then the forced response due to the nature of the force response, everything should be at that exact same frequency. So just as a quick example, and I know that you guys have done this, it's just good practice. Let's say that we had a signal Vx of t was 15 cosine 2 pi t plus 60 degrees volts. The phasor representation of this, capital Vx, we would simply keep the magnitude 15 and take the phase angle of 60 degrees and have our phasor representation. Easy peasy. And we can go back and forth, right? So if we have a phasor domain number and we know the frequency, we can absolutely go back to the time domain sinusoidal representation. We in this class are going to be using cosine as our basis, meaning that if we had a current Iy of t that was, let's say, 45 sine 60t plus 11 degrees milliamps, the phasor domain representation of this would be 45, and we would have to subtract 90 degrees from our phase angle in order to convert that sine function to a cosine function. So that would be negative 79 degrees milliamps. So we're always using the cosine as our basis. So we have a fundamental definition for a phasor voltage, and we have a fundamental definition for a phasor current. So now let's use those things to develop some relationships for simple circuit components like capacitors, inductors, and resistors. If anybody has any questions about any of this, feel free to stop me and ask, because we are one day ahead. So we got time to spare if it will help clarify things. All right, so let's start with a resistor. So if I have a resistor, with a value of R, I'm going to define the positive polarity terminal to be on the left-hand side, like so, and the current IR of T will be flowing into the positive polarity terminal so that my resistor is obeying the passive sign convention. And I'm going to try to develop relationships using our generic time domain relationships and then applying what we know about frequency domain signals to develop a relationship. So if VR of t is of the form Vm cosine omega t plus some phase angle theta v, and IR of t is equal to Im cosine omega t plus theta I can now use use the definition of phasors and mixed signals to develop a frequency domain relationship. So what do we know about the relationship between the voltage drop over a resistor and the current flowing through that resistor? What Ohm's law, exactly. That's Ohm's law tells us exactly how those two things are related to each other. As a constant of proportionality, we know that V of t is equal to R times I of t. Well, if we use our mixed domain representation for V of t, we would have Vm e to the j omega t plus theta v is equal to r times Im e to the j omega t plus some phase angle theta I. There is I'm going to do this explicitly this time. I'm going to break my exponential function up into the sum of two exponential functions. So e to the j omega t plus theta v can be written as e to the j omega t multiplied by e to the j theta v. And I can follow suit on the right-hand side. Like so. And I can observe that there is a common factor of e to the j omega t on each side of my equal sign. So this is me suppressing the frequency term. Frequency is common between the two things. And I'm left with a relationship Vm e to the j theta v is equal to r times Im e to the j theta I. Using our fundamental definition of phasors, Vm e to the j theta v is just an arbitrary theta voltage V is equal to an arbitrary phasor current I multiplied by the resistance value itself. So Ohm's law in the frequency domain is the exact same thing as Ohm's law in the time domain. We simply use phasor voltages and phasor currents. Another thing that we can infer from this relationship is that theta v has to be exactly equal to theta I, right? We have complex numbers on both sides of the equal sign. So the magnitude of the left-hand side has to equal the magnitude of the right-hand side, and the phase angle of the left-hand side of the equal sign has to equal the phase angle of the right-hand side as well. So we know that the magnitude of the voltage drop is equal to R times the magnitude of the current, and we can easily see that the phase angle of the voltage is exactly equal to the phase angle of the current. So for a resistor, currents and voltages are perfectly in phase. Now let's consider the case of an inductor. We have L. Here's IL as a function of time. Here's VL as a function of time. What is the relationship between current and voltage in an inductor? And let's do the derivative-based one because it'll be less ugly than the integral-based. Yes, so the voltage drop over our inductor is equal to L times the derivative of the current flowing through our inductor. So substituting in our mixed domain signal, we have Vm e to the j omega t plus theta v is equal to L times the derivative with respect to time of Im e to the j omega t plus theta I. If we perform this derivative, this leaves us with j omega L Im e to the j omega t plus theta I. Suppressing our frequency terms gives us Vm e to the j theta v is equal to j omega L Im e to the j theta I. So we could express this as V phasor is equal to j omega L times I phasor, which is a fundamental relationship. Another thing that we could do is we could represent the imaginary number j as a polar form complex number. So as a quick aside, what I mean by that is, let's say that we have a complex plane here, okay? Where this is our real axis, and this is our imaginary axis. If we go out 1 unit in the positive real direction, expressed as a rectangular number, that is 1 plus J0, and expressed as a rectangular number, or excuse me, a polar number, that is 1 angle, 0 degrees. Well, if we go up 1 unit in the imaginary direction, in rectangular form, that is 0 plus J, or 1 angle 90 degrees. -1 would be -1 plus J0, which is 1 angle plus or minus 180 degrees. And lastly, -J, or 1 in the negative imaginary direction, would be 0 minus J, which is 1 angle minus 90 degrees. So, recognizing that this J is the exact same thing as 1e to the positive 90 degrees allows me to rewrite this as, omega L Im e to the j theta I plus 90 degrees. And so I did this explicitly so that we can see the angular relationship. So theta V is exactly equal to theta I plus 90 degrees. We're going to use this relationship frequently, so I wanted to explicitly show you where it comes from. All right. Lastly, we have capacitors. And so we know that for a capacitor, the current IC of T is equal to the capacitance value times the derivative of the voltage. And so this gives us Im e to the j omega t plus theta I is equal to C times the derivative with respect to time of Vm e to the j omega t plus theta V. When we take that derivative, this leaves us with j omega c Vm e to the j omega t plus theta V. Suppressing our frequency terms leaves us Im e to the j theta I is equal to j omega c Vm e to the j omega, e to the j theta V. Which yields the phasor relationship. Phasor current I is equal to j omega c times phasor voltage V. And again, doing the thing where we say that j is the same as 1e to the positive 90 degrees means that we can express this as omega c Vm e to the j theta V plus 90 degrees, which tells us that theta I is equal to theta V plus 90 degrees. So these are our simple current voltage relationships in the frequency domain for resistors, capacitors, and inductors. Let's take this one step further and now talk about impedance and admittance. All right. So because we are dealing with AC and now phasor quantities, we are going to have to redefine effectively the ratio between voltage and current, right? So if we had a DC circuit, DC black box circuit like so, if we applied some test voltage source, or we could do a test current source as well. So this is going to be VS, and this is RS for, I'm just treating this as a practical source for all intents and purposes. We know that the resistance of the DC black box circuit is simply the voltage drop over the black box circuit under test divided by the current flowing in to the black box circuit, right? So the resistance of the black box circuit is defined as Vx divided by Ix, which is just purely Ohm's law performed experimentally. If we do the same thing for a phasor circuit, so now we have some AC black box circuit over which we apply some test voltage VS phasor. The ratio of the phasor voltage drop across the terminals of our AC black box network divided by the phasor current flowing into our black box network is what's known as the impedance Z. Z is a complex number, but it is not a phasor, so I'm not going to put a bar over it. So Z fundamentally is the ratio of the phasor voltage to the phasor current. And we can express this relationship in two different ways. So recognizing that the phasor voltage is simply the magnitude of the phasor voltage with some phase angle theta V, and the phasor current is the magnitude of the phasor current with some phase angle theta I, we can express this as Vm over Im with an angle of theta V minus theta I, which we can treat as the magnitude of Z with an angle of theta Z. In rectangular form, this relationship can be expressed as R plus JX, where R is the real part of Z and is known as the resistance. And X, is the imaginary part of Z, and it is known as the reactance. We'll get into this in much more detail in a bit, but inductors have a positive reactance and capacitors have a negative reactance. We can use that to classify the behavior of an unknown connection of elements, whether it behaves inductively or capacitively based purely on the sign of the x value here, which also turns out to relate exactly to the sign of the angle theta z in the polar form of the impedance. We can go back and forth between the rectangular and polar forms using the following relationships. I'm just going to put them over here. So the magnitude of Z is simply the square root of the resistance squared plus the reactance squared. The angle of the impedance is the inverse tangent of the reactance over the resistance. And if we want to go the other way, the resistance is the magnitude of the impedance times the cosine of the angle, and the reactance is the magnitude of the impedance times the sine of the angle. So we can flip-flop back and forth between the two trivially. So using our fundamental definition of impedance, we can then develop relationships for impedance for resistors, capacitors, and inductors. And this is where things become very, very useful. It's this step that allows us to treat our steady state sinusoidal circuits as simple DC circuits just operating in the frequency domain. So for a resistor, by definition, it's going to be the phasor voltage drop over the resistor divided by the phasor current flowing through the resistor is just the resistor value itself, which we can express as R plus J0 ohms in rectangular form is identical to R angle 0 degrees ohms in polar form. So resistors are a purely real impedance. For an inductor, the ratio of the phasor voltage divided by the phasor current is J omega L. So this becomes 0 plus J omega L ohms in rectangular form, or omega L angle, positive 90 degrees ohms in polar form. And lastly, for a capacitor, the impedance is given by 1 over J omega C, which looks like 0 minus J divided by omega C ohms in rectangular form, or 1 over omega C angle minus 90 degrees ohms in polar form. Just to make sure that we're all on the same page here, does everybody understand how 1 over J is the same as negative J over 1? We all okay with that? All right. So these are our different impedances for resistors, capacitors, and inductors. They all have units of ohms, which means we can treat all of them as if they were resistances in a DC network. So combination of impedances in series, add like resistors in series, impedances in parallel, add like resistors in parallel. We no longer need to say, well, inductors in series, add like resistors in series, and capacitors in series, add like resistors in parallel. All that jazz can be thrown away. Everything is a resistance effectively now. All right. The next topic that I would like to talk to you all about is the concept of admittance, which you may or may not be familiar with. Okay. Admittance is used a lot in network theory, which is something that you'll be getting into significantly more, a lot in your senior year here. But I want to kind of introduce a few things right now. So admittance, its fundamental definition is simply the reciprocal of the impedance. So from that, it is the ratio of the phasor current divided by the phasor voltage, which gives us Im angle theta I divided by Vm angle theta V, or Y with an angle, sorry, take one more step here to make it perfectly clear. Im over Vm angle theta I minus theta V, which is the magnitude of Y with an angle of theta Y, where we can easily observe that theta Y is simply negative theta Z. There's a relationship between the phase angle of the admittance and the phase angle of the impedance. So this is the rectangular form representation. We can also represent it in polar form as G plus JB, where G, how did I do this? I want to be consistent. All right. G is the real part of Y, known as the conductance, and B is the imaginary part of Y, which is known as the susceptibility or susceptance. Susceptance. All right. And we can get the simple relationships that the magnitude of Y is the square root of G squared plus B squared. The phase angle theta Y is the inverse tangent of B over G. G is Y cosine theta Z, and B is the magnitude of Y sine theta Z. One thing that I want to point out, and will express it momentarily, is that conductance here in AC circuits is not the same as conductance in DC circuits, right? In a DC circuit, we define conductance as simply the reciprocal of the resistance. The conductance, which is the real part of the admittance, is not simply the inverse of the resistance, okay? So I want to make that really, really clear. So we know that G plus JB is equal to 1 divided by R plus JX. This gives us 4 relationships. G is equal to R divided by R squared plus X squared. B is equal to negative X over R squared plus X squared. So this is telling us what our conductance and susceptance are in terms of our resistance and reactance. And we can go the other way around as well. Resistance is G divided by G squared plus B squared. And lastly, X is equal to negative B over G squared plus B squared. So using the definition of admittance, the admittance of a resistor is simply phasor current divided by phasor voltage is 1 over R, which means we have 1 over R plus J0 Siemens, or ohms to the negative 1, in rectangular form, which is 1 over R angle 0 degrees Siemens in polar form. For an inductor, we have 1 over J omega L, which is 0 minus J divided by omega L Siemens in rectangular form, or 1 over omega C angle minus 90 degrees Siemens in polar form. And lastly, for capacitors, we have J omega C, which is 0 plus J omega C in rectangular form. And finally, omega C angle positive 90 degrees Siemens in polar form. So admittance, or excuse me, impedance, which you all should be very familiar with, and admittance, which may or may not be new depending on if you had me or Davis, or, and what videos you decided to watch last quarter. All right. I would argue that until you actually get into your network theory classes and stuff like that, where impedance, or excuse me, admittance is going to have some real use, convert all admittances into impedances and then just work from there. It'll make your life easier. Really, admittances only pop up when you start dealing with 2-port network transfer functions and all that kind of stuff, which are beyond what we're going to talk about in this class by a pretty significant degree. So once you get into that relationship, when you're talking about how to treat a motor from a certain perspective and all that jazz, admittance doesn't really do you a heck of a lot of good. I think in your homework questions and stuff like that, I ask you to analyze a network and tell me what the equivalent impedance is and then the equivalent admittance is. If you find the equivalent impedance, just take the reciprocal to get the admittance. Don't do any fancy work or anything like that. Okay, so does anybody have any questions on the converting time domain signals? Yes. The admittance of, oh yeah, right here, that should be an L. Thank you. Just crappy handwriting, I think. Yes, thank you very much. That should be an L. All right, any other questions regarding converting time domain sinusoidal signals into frequency domain phasors, or regarding phasor domain relationships for current and voltage for capacitors, resistors, and inductors, which includes then obviously admittance and impedance. Anybody got anything? All right, then back to pretty much full on review. Oops, I ran out of pages there. Let me circle back around to page 1 here. Let's talk about some simple AC steady state circuit analysis techniques. We got 30 minutes left. We probably won't even use all 30 minutes on this, okay? So let's say that I have the following steady state sinusoidal network. So this is SSS Circuit Analysis. So because we've all had experience converting a time domain circuit into a frequency domain circuit, I'm just going to start with a frequency domain circuit here. So let's say that we have the following circuit. And I'm going to define some currents. There's a phasor current I1 that we might be interested in, a phasor current I2 that we might be interested in, a phasor current I3 that we might be interested in, and I'm going to give you some voltages as well. So a phasor voltage V1 that we could be interested in, and a phasor voltage V2 that we could be interested in. So because this is largely a review, how could I go about solving for these quantities? Anybody have any idea? Okay, so we could combine everything into a single equivalent impedance and then use Ohm's law. That would allow us to calculate the quantity I1 pretty easily. So that is definitely one way that we could do things. We could use mesh or nodal analysis. That would require us to set up a system of equations, which we may not be able to solve by hand. So it might involve the use of the computer, but that's nothing wrong with that. Anybody got any other thoughts? Okay, so we could do a source transformation on the practical voltage source on the left, which would allow us to use current division to calculate the quantities I2 and I3 really easily. Yeah, then the voltage would be easy, and then we could use KCL to figure out what, so I1 would be equal to, based on this schematic diagram, I1 would simply be equal to I2 plus I3, so that would work. So the short answer here that I'm really looking for is what you guys just did. You can do any damn thing you want, right? Whatever you're comfortable with in these type of circuits will absolutely work. Now the level of the level of complexity that we're going to have in the circuits that we'll analyze in this class are going to be kind of cranked up a notch from what you saw in circuits 1. So we're going to do a lot more involving the use of computers to solve nodal and mesh analysis and stuff like that. So I'm telling you explicitly right now, even though you haven't even turned in the take-home portion of exam 1, for the take-home portion of exam 2, there will be a gnarly circuit in which you will have to do both nodal analysis and mesh analysis on your computer and solve it. So I'm just telling you right now, if you have not yet gotten MathCAD, I don't know how or why, but get it and start asking questions about how to use it if you're unfamiliar. Yes, sir.
Question about the take-home portion.
Sure.
We do it in the exact same format somewhere.
Yep, absolutely.
It asks, the very first question is asking to use the, well, I don't know if I'm allowed to talk about it, but
I think it's asking you to use a practical op-amp model. Yeah.
I wasn't sure if we were supposed to write it out.
Yeah, draw it out.
Yeah.
And then set up the system of equations.
On the computer, so I was just like,
Yeah, draw it out, set up your system of equations, solve said system of equations, tell me what the voltage at the output or whatever the heck it was I asked for. It's a good way to check whether or not you're on the right track there, even though it's not an ideal op-amp circuit. So I think I had Rn as being something on the order of hundreds of kiloohms. Does that sound about right? Yeah. And R out being on the order of a couple of kiloohms. So Rn is much smaller than it should be, and R out is much larger than it should be. It should work out to where things are probably within 10% of what you would get using ideal op-amp analysis. So that's a good way to check whether or not you're on the right track there. You know how it should behave if it's an ideal op-amp. The practical op-amp should be close, even if it's a crappy practical op-amp. Does that answer your question?
yes.
Okay. So, of the 3 methods or several methods that we talked about here, I think the one to me that seems the most fruitful with the least amount of work is Mr. Burrell, I believe, suggestion of doing a source transformation, which will allow us to determine 4 of the 5 quantities trivially, and then KCL lets us get the last one. So let's take a stab at that real quick and then call it a day. And we'll get into the harder stuff when we get back from the holiday on Wednesday. So who remembers how to do a source transformation? Let's start there.
You would turn the current into or V over I, or V over R.
Okay, so turn the voltage source into a current source. All right, I am on board with that. All right, so what's 24 angle 60 divided by 4 angle 0? 6 angle 0. Oh, so, excuse me, 6 angles. My apologies. Yeah.
And then you would put it in parallel with the same.
So let me ask you a question. I1 is listed as the current flowing through the 4 ohm resistor. Can I safely say that I1 is the current flowing through the 4 ohm resistor now after I've done that transformation? Absolutely not. Okay, I want to be very, very clear about that. I1 is defined as the current flowing into this resistor network. So I can make all the changes I need to this impedance network over here on the right-hand side, and I1 is still okay. But as soon as I move that 4 ohm resistor's position in the circuit, I1 no longer exists. So I want to be very, very clear about that. All right. So then we're just going to reconnect it to what was left. So that's this J6 ohm impedance, where this is the phasor current I2. This is the phasor voltage V1. Here is my 8 ohm resistor. Here's my minus J4 ohm impedance. Here's phasor current I3, phasor voltage V2. All right. So now what can we do?
At this point, you would be able to easily say that V1 is defined voltage as 1 of them, but it's equal to
Okay.
Or if you just want to keep 8 ohms, if you
So I understand, I think I understand what you're saying, at least to some extent. So you can combine the 8 ohm resistor with the minus J4 ohm capacitor into a single impedance of 8 minus J4 ohms. But if you do that, you lose that quantity V2.
Well, you could just find the current going through it.
Okay, so if you found the current I3, then you could just use Ohm's law to get that voltage V2.
Yeah.
So how could we find the current I3 and or the current I2 easily here? Because what you started talking about, I think, was combining the things that are in parallel,
yeah,
which we could do, absolutely, but how would that be different than finding the equivalent impedance before we did the source transformation? It would, the source transformation allows us to determine those two currents in a trivial way. You're just not seeing it yet. Current division, absolutely right. We have a current source in parallel, or excuse me, current source in parallel with 3 impedance branches, or however you want to express it. So I could find the current I2. How? Somebody remind me how to do current division.
So 6 angle 60 J6 over, sorry, 1 over J6 over 4, or sorry, 1 over 4 plus 1 over J6 plus 1 over 8 plus or 8 minus.
All right, that's correct. And then we could do some math here, which I think my best guess is I've done. We're finding I2, right? 2.71, sorry. With an angle of negative 11.59 degrees amperes. Does this methodology look unfamiliar to any of you? Let's start there. The reason why I say that is because some people teach current division differently than I do. I typically teach this method, which is valid for an infinite number of branches in parallel, where you use 1 over the branch you're looking for divided by 1 over all of the branches added together. But some of you may have seen something that might look like, let's call it let me do that, where it doesn't have the reciprocals of things. That methodology only is applicable for 2 branches in parallel. So we have more than 2, so we couldn't use it even if we wanted to. And also notice that if we were trying to find the current through the first branch, the numerator is the resistance in the second branch, the one we're not interested in. So that one just gets real wonky real fast when trying to do multiple things. So you could technically do 4, so 12 minus J4 divided by 4 plus 8 plus J6 minus J4 would work, but it's just real weird putting everything you don't want in the numerator, or to me it is anyway, everything you don't want in the numerator divided by everything in the denominator just screws with my head. So I much prefer the reciprocal method. I just wanted to make sure that you guys have all seen it before, because not everybody teaches it that way. All right, so now that we know I2, figuring out V1 should be trivial. J6 ohms times I2, 16.26, angle 78.41 degrees volts. We could find I3 now easily using current division, 6 angle 60 degrees amps times 1 over 8 minus J4 divided by 1 over 4 plus 1 over J6 plus 1 over 8 minus J4 is equal to 1.81 angle 104.97 degrees amps, which lets us trivially find V2 minus J4 ohms times I3, 7.27 angle 14.97 degrees volts. And lastly, now that we know all of that information, we would have to go back to our original circuit to find I1, because I1, again, does not exist once we've done that source transformation. So how do we find I1 here? I2 plus I3, just good old Kirchhoff's current law at that top middle node. .5, if I can read my handwriting correctly. Yeah, 2.5 with an angle of 29.06 degrees amps. We can beat simple example problems like this to death all day, but we did these in circuits 1 and all that jazz. So I don't want to say it's a waste of time because you could use some practice, but it's not particularly intriguing and we only have 10 minutes left. So I'm fine with leaving a little bit early. So with that in mind, does anybody have any questions about any of the sinusoidal steady state analysis? It could be a question that maybe you didn't have answered when you took circuits 1 last quarter or previously that you want me to address in the coming days or anything like that. I'm happy to answer it. Like I said, we are 1 class period ahead of time. We might technically be like 1 1/3 classes ahead of time now. So I'm perfectly happy slowing down when we get to something where people want some time to think about things. So feel free to ask questions and all that jazz. Otherwise, we're going to get to some gnarly 3-phase power circuits just to fill time. Just saying. All right, unless anybody has anything, I'll see you guys next Wednesday. If you have any questions regarding your take-home exam, feel free to shoot me an email over the weekend, and I will try to respond while I'm not playing video games. Oh, if you could please sign this. Thank you.